Let's get started. So, hello, ladies and gentlemen. My name is Christian Macario, and I manage the semiconductor segment and networks. And part of my role is about making sure that semiconductor engineers have all they need to tackle their daily challenges. Before networks, I worked in both design and verification positions at NXP and ARM. And today, together with my colleague Baruch, we will talk about how many leading semiconductor companies have been improving their verification methodology by integrating MATLAB and Simulink into their workflow. And this allows them first to start verification early at system level before any RTL or SPICE netlist is available. And that's what we call shift left verification. And we heard the shift left term already today in the afternoon keynote from Vicky Mitchell from ARM. And also in the morning in the tutorial from Manfred Tanner. So that's something that the industry is really trying to do, moving verification early, either to find bugs early or moving the development flow early and enable the end users of our devices. And when it comes to verification, shifting it left is not enough. We also want to reuse all what we do at system level throughout the entire design flow. So we want to reuse models and test benches that we use at system level. Also at implementation level, RTL and SPICE, depending whether we are designing, whether we are analog or digital designers. But we might also want to reuse all the stuff we have in post-silicon activities like testing and characterization, for instance, and there are companies doing this. We will see some examples later. So regarding verification at system level, how we do it and why we should do this. So this approach is based on behavioral models, and we will see how we can easily build test benches around them, run regressions, analyze coverage and trace requirements. And this allows to find bugs as early as they are introduced. And another big advantage is that this approach promotes automation and reuse, reducing the needs for textual specification, which is often source of bugs. And yeah, if you have any questions during this presentation, please type them into the chat window, and we will address them during the Q&A session at the end. And yeah, in any case, you can find our contact details here. And feel free to reach out to us at any time. All right, let's get started with the presentation. Like this. Here we are. So this is the agenda for today. First, I will give an overview of the workflow, how it looks like, and why should you consider it. Then we will see how to set up test benches and verify MATLAB code. After that, we will do the same for Simulink, and we will notice that in this case, the approach offers more options and is more complete if compared to the pure MATLAB approach. And after that, my colleague Baruch will take over and will describe how we can reuse MATLAB and Simulink models and test benches within EDA tools. Finally, he will show some results from some of our customers, and we will have a summary at the end. All right, let's start with some words about the workflow. So first of all, verification is about catching bugs. And to better understand the problem, let's analyze the root cause of silicon bugs. This is the result of a survey run by Wilson Research Group and commissioned by Mentor Graphics. And we see that two main contributors to bugs are specification related. This means that bugs are introduced early in the design flow at a specification level, and they are usually catched much later at RTL verification or at system integration level. So how can we improve our verification flow to catch early bugs and avoid long iterations? So this picture illustrates the traditional semiconductor design flow. Most of you probably are familiar with such a workflow. So we start with some research and some market requirements. We define the system architecture, then the different IPs and algorithms. And after that, we start with the implementation phase. That can be digital, analog, or software, can be RF as well. And that's basically when verification starts. So, and after that, we have a system integration phase where we really put together all the digital, analog, and software together, and we verify that everything works together. So in such workflow, we see two main limitations. First is that verification is started very early in design flow, which is starting at implementation level. And second, we see many manual steps. The information is exchanged with written documentation, which is not ideal. It is bug prone and makes all design iteration long. Whenever you have a requirement changing, it takes a long time to propagate it through the design flow. So many semiconductor companies, as I said before, have been working on improving such a workflow by starting verification early and improving the reuse between the different design steps and replacing partially these textual design, textual specification steps. So basically moving to a workflow which looks more like this, that we call model-based design, which is a workflow based on behavioral models that are reused throughout the design flow. So such models are executable to allow multi-domain simulation and early verification. And with multi-domain here, I mean really analog and digital and software all together. So this helps finding early bugs before they propagate down into the workflow. Before we have seen that many bugs are specification related, and by operating like this, we can really find them much earlier in the design flow compared to a traditional workflow. And it also facilitates design space exploration, as we can model and simulate all together, all analog, digital all together. We can also, it's also easy to try different architecture, to try different speeds between hardware and software, etc. And another thing we allow is requirement tracing. So we can interface to a requirement database software and allow tracing requirement in this workflow. So then all models and test benches designed using this approach can then be reused within the traditional EDA tools for analog and digital design. So specifically, we can reuse them in verification. So this applies to design models as well as test bench components. For instance, analog models designed using MATLAB and Simulink can be reused within digital RTL simulators, as well as within analog SPICE simulators. And the same applies to test bench components and for digital models. So for instance, one way to use this is to, if you want to generate a 5G compliant waveform, that's very easy in MATLAB. While doing SystemVerilog might be quite tricky, right? So you can do it in MATLAB and integrate it in your digital test bench, for instance. Another way to use this in a smart way is you can take analog models and integrate into digital EDA simulators, so at RTL level as a test bench component. So it can help you bridge between different domains, analog and digital. And also, if you're a digital designer, you can take the digital model here or the model for the digital part you're designing and use it as a reference model in your RTL simulators. And the same applies to test benches. So stimulus generators, core boards you design in MATLAB and Simulink, you will be able to reuse them in EDA simulators. Then that's not the only way to reuse models. Design models can be reused by generating RTL code and systemcTLN models. And other EDA interfaces are available as well. And these allow to feed implementation information back into the models, like information coming from RTL or SPICE simulations or from the lab, from the measuring equipment can be fed back into the models to make sure that models are aligned with the implementation as well as the real hardware samples that you get after tape out. Now let's see some details about how all this can be implemented, starting with verification of our MATLAB code. So a good way to structure verification of MATLAB code is to use the so-called unit test framework. So interesting enough, Moshe Zaltberg from Verist in this morning's keynote talked about the importance of unit test frameworks. So in case of MATLAB, this framework standardizes how tests are written, run, and reported. And it forces to separate verification from design. And it basically manages the 4 basic verification steps, which are set up to initialize the code or the system, the actual execution, the verification of results from execution, and the teardown phase, which is basically the opposite to setup. It also integrates with other tools like continuous integration tools, which is particularly important if we want to be more agile, as it was described in this afternoon's keynote from Vicky Mitchell from ARM. So going back to the unit test framework, this supports different approaches, and the simplest and easiest one is script-based. We define a script and we split it into sections, and each section being a test case. We use the assert function to define the pass-fail criteria, like here and there. And we can run all our test cases using the run test functions. Another approach is function-based, where each test case is implemented as a function. To get even more capabilities like parameterized testing, we can use a class-based approach. This way, we will be able to easily run our test cases in all the allowed combination of parameter values. And on top of that, we can use a full library of qualification functions to produce 4 different types of test failures. For instance, we can produce verification or fatal assertions. And we can also tag our test files in our project, making it easier to find them and allowing to automatically run them and run all the test cases. And this is particularly handy in case we want to integrate MATLAB within continuous integration systems. So we have some different ways to define test cases and to run them. But how do we quantify how good our verification is? And the answer is easy, by enabling coverage that allows us to see which parts of the code have been actually stressed. So basically, we can do all of what we usually do at RTL level. We can do it earlier in the design flow to verify our models more at system level. And then we will see, Baruch will show how we can reuse all what we have been developing in MATLAB and Simulink within EDA workflows. So we talked about continuous integration. These systems are getting more and more popular within the semiconductor workflows, and many companies are integrating MATLAB and Simulink within such systems. And please notice that this applies to both MATLAB and Simulink workflows. Now let's move to Simulink verification or Simulink-based verification. And let us start with a few words about Simulink, as not everyone might be familiar with it. So the first thing that you notice when you use Simulink is that it's a block diagram-based environment. And that allows, it allows to model, simulate, and analyze multi-domain systems. And as I said before, with multi-domain here, I mean really digital, analog, RF, and software all together if needed. And modeling can be done using multiple abstraction levels, from transistor level up to algorithm and mathematical level. And as MATLAB, Simulink allows you to generate code like C and C++, but also, as I said before, RTL code, as well as SystemVerilog and UVM behavioral code. It can also integrate existing C and Python code, and it can interoperate with domain-specific tools like EDA tools. And this part will be described in the second part of this tutorial by my colleague Baruch. Now, MATLAB and Simulink are not two separate worlds, but they can work together. And here are some ways to implement such a interoperations between the two tools. Now, going back to verification, using Simulink, we can easily set up test benches and create test cases at different levels in our design hierarchy. So basically from unit level up to system level. And we can also define our verification plan, run regressions, and generate reports. Again, in order to measure how good our verification is, we can collect and analyze coverage. And results can be displayed within the block diagram, where blocks with less than 100% coverage are displayed in red, and blocks with 100% coverage are displayed in green. Or it can also, you can get the same results, even well, better results or more accurate results into a detailed report, a detailed written report, with more information about what has been covered and what not in your model. So what Simulink offers is also a formal engine that allows you to uncover design inconsistencies, prove formal properties, and also automatically generate test cases to close your coverage. So we have seen at the beginning of this presentation that requirement change is one of the main sources of bugs. And that's one of the reasons why requirement traceability is important. Many of our customers have been using our tools to import requirements from an external database, refine them with Simulink, link requirements to functional blocks and to the test cases. And this allows to generate a traceability matrices. And after that, this information can be exported back into the main requirement database. And if you are generating codes from our models, either C or C++ or RTL code, the requirement information is propagated down to the generated source code as a comment. And for people working in automotive projects, it is important to be compliant to functional safety standards like ISO 26262 or SOTIF, etc. So MathWorks tools have been pre-qualified for such workflow scenarios. And we also have developed a reference workflow that helps our end user to be compliant to functional safety standards and to generate the needed documentation. All right, now let me hand over to my colleague Baruch, who will show how we can reuse all what we have been, what we have seen until now into the EDA tools. Baruch, the stage is yours.
Thank you. Thank you, Christian. Can you stop sharing and I will start sharing my screen?
Sure, here you are.
Great, thanks. Yep, so one moment. And sharing. So I hope you see the screen now. And let me start. So let me start with introducing myself. My name is Baruch Mitzengender, and I'm an application engineer at the Munich office of MathWorks, working mostly with our HDL-related tools. Previously, I was a basic design verification engineer in various companies. And yes, so Christian, of course, mentioned that's throughout the day. If you have any questions, please post them into the chat or the Q&A windows, and we will refer to them at the end of the presentation. So let me start with an overview of the flow, which is similar in both MATLAB and Simulink, as Christian has also already mentioned. So after building our model and verifying, as was described just now, you will probably like to utilize the environment and reuse the work you've already invested in, also in the implementation phase. So the first thing that you can do is to utilize the co-simulation functionality, in which you drive the same stimuli in parallel into your model and into your implementation, while comparing your outputs, right? So don't forget that at this stage, your model is already verified to your satisfaction. That's the part that Christian was just describing. And now it's actually your kind of golden reference. That's what you compare to with your results. The meeting part, if anybody, okay, great. Yeah, so you can use co-simulation in both digital and analog simulators like Cadence Spice, QuestaSim, Cadence Exilium, or previously Incisive, etc. Another important capability is the generation of SystemVerilog DPIC components. Those components, if you're not familiar with them, follow the SystemVerilog standard and are basically a SystemVerilog wrapper around C files. Okay, so as we can generate C code from practically almost any MATLAB function or any Simulink block, the DPIC flow allows us to simulate together in one simulation, be it digital or analog, all components together as a whole design. Already in early stages, when not all analog and digital blocks implementations are already available. So already in the prototyping stage or the algorithm building before it's really elaborated, etc. So this kind of capability can prevent bitter integration surprises later on. So, you know, as the later you find a bug, the more costly it might be, the more deterministic it might be for the project. Definitely, if it's a small company, also might be even for the existence of the company. So, of course, the biggest value is to try to verify as early as possible and try to find bugs, especially crucial bugs, as early as possible. That's a generous mindset, I guess, that all of us have it. So anyway, those coming back to the DPIC part, those SystemVerilog components can also be used in a UVM environment that we also have building, and I will be talking about it in a couple of minutes. Last but not least, HDL code generation. So though it's not the main topic of the conference, so it's design and verification, but somehow it's much more verification in DVCon, but still we have a design part, right? So HDL code generation is I think an important capability. And while you can use all the methods I've just described, co-simulation, DPIC, etc., on testing manually written code or legacy code or whatever code that you get from anywhere, why not to generate a fully synthesizable code from the golden model you've invested so much in building? So you can generate from your models a synthesizable RTL cycle and bit accurate, be it Verilog or VHDL, and be sure there will be no typos included, right? So smiling a bit, but yeah, that's not something that you will have, obviously. And actually having this full flow of modeling, model verification, code generation, and code verification done within MathWorks tools will most probably help you even substantially in your certification processes, assuming you have such processes with your projects. And as I mentioned also, it is possible to, if you have parts of your code that is either manually written, legacy code, or third-party code, also if it's all, you can basically code that is already verified, a standalone, as the block itself or the parts are already verified, you can include this code as a black box inside your Simulink environment and verify the whole design functionality together with the black box. So it's not preventing you don't have to do everything in the Simulink, and still generate the code for the new parts and integrate the let's call it older verified code within your big environment and use it in the project. Now let's talk about the SystemVerilog component generation, the DPIC, which I was just mentioning. So HDL verifier basically uses a MATLAB coder or Simulink coder to generate the C models, which are DPIC. And as you can see it, so you can reuse these models for the verification part. You go from the MATLAB and Simulink environment here on the top part of the screen here, and you generate the DPIC, for example, for the scoreboard, you can do it for the driver, and you have here the DOT internally, and you reuse basically the verification environment and verification models and test benches that you used in the early stages, also later on in your SystemVerilog environment. Everything is automated. You generate the code and SystemVerilog interface with a few button clicks, and you generate the make files and the shared library files, DLLs, etc. All is done for you basically. And anywhere, as I mentioned already in the previous slide, anywhere C code can be generated, you can wrap it with the SystemVerilog DPIC. So digital, analog, RF, also things that of course are not synthesizable. You can generate a SystemVerilog around them. Of course, the SystemVerilog is not synthesizable, right? It's behavior, but it definitely works fine for your purposes for verification. Just to differentiate, the HDL code generation that I was talking and will be talking again about is synthesizable. So there are two aspects to that we need to have in mind that, of course, we talk about different things. Now, there is also the UVM testbench generation with a command that's called UVM build. And in this one, we basically, with this command, we basically generate the SystemVerilog top model, so kind of skeleton for the UVM environment. So everybody that is familiar with SystemVerilog, and I guess many of you do, know that that it's many blocks are involved, many files are involved. It's kind of complex environment. So we can provide you the skeleton on which you can hang or expand your functionalities on top of it, and for the scoreboard and sequencer and driver, etc., and to connect it to the DOT and the monitor and all that. So that's basically done by us for your benefit. Similar approach to kind of mirror approach to the DPIC part, where you can generate SystemVerilog for different parts of your model. You can also generate SystemC TLM component generation in order to verify your environment in the software environment together with your software component. So again, it's something that allows you to do verification of your system software and hardware together in early stages of your design, and of course growing with it. But already in early stages, you can kind of test the integration of the different components that you have already. How do they work together? Maybe also stating the obvious, the most bitter surprises are when each component is working good by itself, but then when you integrate them, you find out that they don't work well together. So this kind of approaches, the DPIC and the SystemC parts, and in general, all the multi-domain verification that we are talking so much about is minimizing the chance for such nasty surprises at a later stage of a project. Now I'll talk about the HDL code generation. So as you can see here written, we generate bit true and cycle accurate HDL that is completely synthesizable. We do it from Simulink, we do it from MATLAB, we do it from Stateflow. Stateflow is state machine tool that can describe million more state machines, so we can generate HDL from that, and it can be HDL, meaning VHDL or Verilog. We don't care. It can be, we prefer, let's call it like that. It's easier in a way to do it from Simulink, because Simulink is has understanding of timing and it's parallel, but it is also possible to do it from MATLAB, which is a sequential language like software. So both are possible. And we integrate the code that is being generated. We can help you also with generating scripts for your synthesis tools. If it is FPGA, it's completely integrated, but here it's mostly, the audience, I assume, is mostly ASIC related companies. So there we definitely help you also with integrating or passing the code into your different synthesis tools, whichever you use. So basically, I heard it in few presentations that I was listening to today. Everybody's talking about executable spec. That's basically the executable spec. You have a Simulink model or MATLAB model that describes a spec already from the algorithm level. And you go all the way down to the implementation, and it is being passed from one step, from one team to the other without misinterpretation of the documented word. It's all being defined and designed on the model. Code simulation for verification and of HDL source code. So apart from the visualization that that is provided to help you to understand the error code, the error cause, you can see you can integrate the the HDL inside a code simulation environment. So we use QuestaSim and Cadence and the Cadence simulators. Let me admit once. So you can use them and simulate them together in parallel to your golden reference. Also, if it is not generated code, but manually written code. And basically you drive the same stimuli, the same test benches driving both the model and the RTL that you have. And the results are being compared in real time, and you can see if there is any divergence between the two. And that's the main capability of the code simulation. You can do also inspect the model coverage. Christian was mentioning that. So here you have the model coverage kind of metric or report of Simulink. Here you have a similar one from QuestaSim. And that's what you can see also here. So you have some kind of a diagram viewer or a wave diagram viewer from Simulink. And here the lower part, I assume it's QuestaSim. And you can see how it behaves and see exactly by eye to inspect it. You can inspect it programmatically, of course, and you can see that the coverage that you get in the model level is basically very similar to the coverage that you get also on the code that was generated, and that allows you for a kind of seamless move from the model level to the code level verification. Let me continue now with some customers' user stories. So I have here 3 to share. The first one is NXP. Let's read together the title: High Quality Early Verification Based on Realistic Scenarios and Improved Design Efficiency Through Reuse of Verification Artifacts. So their challenge was they needed to simulate the entire multi-domain design, which included RF, analog and digital parts with a realistic stimuli. That means they've needed to generate realistic road scenarios. Again, it's a radar project for automotive. So realistic road scenarios they had to generate to verify the complete radar design. They had to satisfy requirements for this multi-domain design that were dictated by the customer and based on the Euro NCAP scenarios. Okay, so the European testing, automotive testing body that probably all of us familiar with. They also needed to improve the design efficiency. They've done it in the design exploration phase, in the digital design parts, and even in the post-silicon activities like characterization and testing. So they could use the test benches and the stimuli that they used in the design also to test the real silicon, like to drive the same vectors, test vectors into the silicon and see, of course, that it behaves as expected. So basically, they were reusing a lot of different parts in different stages, and that has saved them a lot of engineering time. Okay, the results that they had are they have run why doesn't it show here? So they've run a virtual field trials on realistic road scenarios for the full system early in the flow, basically 1 year before the first silicon, as you can see here written in the here in this part, sorry, written in on the slide. So 1 year before they had the first silicon, and at the bottom of the page, you have the link for the technical article that you can also read later on. And I do assume that you will get the presentation from the organizers of DVCon. The next part that I would like to talk about is from Allegro, who's an automotive supplier. And the title says achieving 0 bugs through early verification. So as you can see on the slide, they say it's their words, it's not ours. We started taking serious look at Simulink model-based design for ASIC development in 2014, so roughly 6 years ago. And they say that the team adoption, basically they reached full efficiency in 2015, so it took them roughly 1 year to get into full efficiency, and the result of it was 0 bugs, so no respins anymore. First time right, again their words. And I do assume that now they continue working with us, of course, and I assume now they're even more satisfied because our tools have also developed and cover more stuff and more capabilities. That's of course an ongoing process. I would like to finish with a quote finish this example at least. I have one more after, from a quote from Jamie Haas, who's a very high-ranking manager in Allegro Microsystems, and that's really together. So rapid innovation under a rapid timeline, that's when the traditional workflow falls apart. And that's what we see more and more with the growing demands of having shorter iterations of projects and incorporating many different IPs and many different third parties and reuse and everything. And that's when the scalability of this process in the traditional workflow is hitting its limits. And that's when people need to start adopting new ways. And this approach of model-based design and starting from the model, verifying the model, and what we are basically talking in this presentation, that's making it much more frictionless, let's call it like that, relatively, of course, and helps a lot in the different processes that you go through when designing. Last but not least, at least for this presentation, last example is from Nokia, faster execution and quality improvements in 5G development. So this story is relatively new. They went with this with this project eventually into silicon, into production silicon. They've achieved a fast execution and execution cycle and the quality improvement. What they did is that they developed a SoC, system on chip, for 5G. So as I said, this design went into silicon. Also here they have used the multi-domain simulation. That's what you can see in the upper screenshot. It's a bit hard maybe to see, but believe me. And in the lower screenshot, we can see actually what they wrote as benefits in their 5G development. So if we look at number 2, getting faster to execution, so faster iteration time, and getting higher quality, so quality improvements and better control of the implications of different changes that they do, be it requirement changes or other things that happen, or bug finds, etc. So it helps them improve that part. And the first part, I wouldn't even ignore that. First, they wrote it, right? So probably it's important for them. And maybe it's even the most important because they put it as number 1. I'm not sure that that's the right interpretation, but basically they wrote visibility and understanding of options. And that's basically meaning that it is beneficial because it's efficient, helping the project planning. It is helping having efficient teamwork, and maybe even reporting to management and visibility of the status of the project and what are the difficulties, etc. Helps the management to understand what's needed, which support, and what's the case here. So these are the case examples. You have also here a link to MATLAB Expo slides. This user story is from 2018, so roughly 2 years old. Summary. So what did we have here in this presentation? So you can start verification already at system level before you have any RTL or any SPICE, also before you have any software. You can measure the coverage, you can trace the requirements. After that, you can connect your design flow, so the shorter iteration cycle of different steps that you need to go, so you can reuse the models in the EDA tools. That's what we were talking now in my part, and integrate MATLAB and Simulink with your development infrastructure. So basically, again, you can reuse the parts that you do in the verification of the model, also downstream in the project, with the code that either you generated or that you use manually, but still with the EDA tools that you verify. So HDR simulators or analog simulators, etc. And this reuse is saving you a lot of engineering time. It actually ensures that you drive the same stimuli that you drove in the model level that you use to make your, or to call your model as golden, as okay, now you're happy with it and it does what you want. You can be sure that you will drive the same stimuli also to the code that you have, and like that you ensure that the behavior, or at least the stage of the code is the same as the model. And these are the main points that I would like to mention. Here I would we arrive immediately into the Q&A, but I would be glad if you could, I will post this link, or maybe Christian, can you do that? Because for me it's jumping obviously, but we will post this link into the chat
Just
window.
done.
Yeah, and there is a very short feedback form for us, some questions that would be glad if you could answer. Yeah, and now the Q&A. So if there are any questions I didn't see, it will be good to get them. And somehow I don't see the chat window, so I have no clue if there are any questions or not.
Well, yeah, I don't see, well, I have it open. I don't see any questions. So if you have any questions, please type them in the chat window. You can access it with the chat button you see on the bottom of your screen. So you can also raise your hand if you want to ask a question without typing, as Israel, our facilitator, wrote in the chat window. All right, I see a question. So what are the advantages when using Simulink in terms of hardware design? So maybe I can give the first crack at it, and then Baruch, feel free to add. So yeah, the main advantage is in case when you have multi-domain systems. So Simulink is very used in mixed signal design. So whenever you have a digital part together with an analog part. And another big strength of MATLAB and Simulink is when it comes to algorithms. So either signal processing algorithms or control algorithms. That's usually the natural place where you want to develop this algorithm, at least early in the design flow. And as we have been showing today, you can develop your algorithms using MATLAB and Simulink, and then you can reuse all what you have done in your EDA workflow when it comes to implementing them as digital or analog logics. Usually, if it's about algorithm, it's usually digital, right? Baruch?
Yeah. Yeah, I can maybe add some points more. So first, one thing that we did ignore here, and maybe it's less interesting, but just to understand how comprehensive is the multi-domain thing, you can, even if you have, you design some kind of controller for I don't know, mechanical stuff or power control or whatever you do with that, or grid, you can even implement a model of your mechanical parts or real world parts, and have it together all in one environment where you can verify the system. Now, the main thing is really, I would say, also shorter iteration time. So you can do design exploration because you can check many times different possibilities and go forward with that. While when you do everything in outside, let's call it like that, in the traditional workflow, everything takes much longer. And the kind of certainty that you get when you have everything in one flow, the kind of certainty that you get that the code that you use eventually in your implementation is behaving exactly the same like the model that you were exploring at the beginning or in the earlier phases of your design and of your project, this certainty is much higher. And that's something that is a very big benefit. And of course, what Christian mentioned, so and myself throughout the presentation, the reuse. So you don't need to do the same work that is done by the algorithm guys and then by the digital guys and maybe analog guys, and then at the end in the integration phase, that each one is working in different environment. You can do all this in reuse, and that's a very big time saver, and of course money.
Yeah, another example of usage of our tools is when it comes to communication systems, you can design and model at system level the entire communication system. So from the digital part of the transmitter down to the RF, to the antenna, propagation channel, receiving antenna, and down to the receiver. So you can really simulate end to end, from bits to antenna and from antenna to bits, your entire communication systems. That's another very common usage of MATLAB and Simulink. All right, any other questions? All right, then I think we can close this session. Thanks everyone for joining, and if you have any questions that pop up to your mind in the next days, feel free to reach out to us.
Yeah, the mail is on the screen. I'll still keep it for a few more seconds, and then I'll sign off. Thanks a lot also from my side for your time.